Hello, I am Utkarsh Kumar Singh from Department of Electrical Engineering, Photonics Lab, Bharati School, IIT Delhi. Today, I'm going to present optical design of wide-angle constant focus lens and electronics assembly for visible light communication. So let's begin. This slide represents the end result of our project. That is, a system consisting of multiple light sources and providing internet connectivity to the mobile devices below. We could compare this communication to any other communication architecture, such as microwave communication, where multiple light sources acts as base stations and mobile devices with microwave antenna could be replaced with mobile devices with Wi-Fi receiver. So here comes our problem statement, which we are trying to solve. We need to have a constant focus for our mobile device visible light communication to work. We have a source emitting paraxial rays here, or simple lens here, converges them onto a single point where a photodiode is placed, which is sensing the light signal and converting it into electrical signal. Now, if we change the orientation of a device in this setup, our focus gets displaced, as you can see here, from there to there. Our photodiode will stop working and will disconnect from the internet. So we need to maintain a constant focus on photodiode even when the orientation of the device changes for flawless connectivity. We need to solve this. We have to have a constant focus on a photodiode at all times. So we are approaching this problem basically into three parts. First, electronic system design. Second, optical system design. And third, the hybrid of both, containing the electronics part and optical part. In future upgrades, we could shrink the size of our whole system and make an optical micro electrical mechanical system. Let's take up the electronic system first. As the orientation of our sensor changes, the focus shifts. If we manually align it to the light source, voila, we are connected again. To achieve this, we could use a pan tilt assembly as shown on this side of the screen, and with a little bit of programming, we could also make it a smart sensor. As you can see, this box represents assembly containing the lens part and the photodiode, and we're going to move this whole assembly automatically so it could get aligned to the light source and have a constant focus at all time. So we used a microcontroller with a camera for image processing, and we're using its data to move a pan and lid assembly with servers to get our sensor aligned with the light source again. You can see a working demo. This is a Raspberry Pi, a microcontroller, add of servers, which is working as a pan and lid assembly. This is the positioning data, and on the right side you can see what the sensor receives, and it's doing all the processing. So it's tracking. As you go right, it goes right, go left, go left. Future upgrades to our electronics approach. We could make this a smart sensor. It could detect the light source, if it's got internet connectivity or not. So we could do this by modding our Wi-Fi protocol with detection parity bits. So our sensor would be able to differentiate between Wi-Fi light and normal light source. We could further work on multi-input, multi-output systems and roaming, and also reduce its size so it could be packaged into a smartphone or a handheld device. Now let's talk about the optical design approach. In the first approach, we move the whole assembly mechanically. But what if we could design such a lens that always focuses on a single point? The light source is here, it focuses here. But even if we move the light source or change the orientation of the device, it focuses on the same point. So first we need to talk about the light sources. You must have seen different types of light sources emitting conversion beams, diversion beams, or paraxial rays. But in case of actual LED, as you can see here, we have simulated an actual test bench LED Osram LW HWQP Ocelon series black flat LED, and it does not have a well-defined wavefront. As you can see, light goes in all direction, and we need to focus such kind of rays on our photodiode for maximum optical power transfer. So here's our lens design. This is an aspheric graded refractive index lens which focuses light from all direction into a single area with equivalent optical power if we move on this area. So this simulation was done in COMSO, and we are still working to improve its performance so we could have a greater field of view. Future upgrades to our optical design part includes optimization and increasing its FOV and adding a parabolic concentrator so that area we're talking about could be reduced to a single point, and also increasing the whole FOV of the system. Once our lens design is completed and our lens is fabricated, we could combine our electronics and optical approach. This will include our lens, photodiode assembly, and a panel assembly with a camera. Combining this, we'll get an optical electrical system that automatically focuses on a single point. And even if the orientation of the device is changed, it keeps you connected to the Wi-Fi network. Once we have completed our hybrid approach containing both electrical and optical part, we could start working on reducing the whole package's size and creating an optical microelectrical mechanical system containing lens, actuators, and a housing small enough to fit in handheld devices such as mobile phones. This summarizes the session. Thank you for your time and patience.